Hello, geometry class, and welcome to this video on section 10.7, inscribed and circumscribed polygons. So I'm going to go through a little bit of what's in the textbook, and then we'll do some problems. So there are a couple of definitions and some theorems to get started, but just so we know the difference, and we've seen this before when we did our constructions, and we found the center of the inscribed circle and the center of the circumscribing circle. So we've seen these words before, but just as a refresher, a polygon is inscribed in a circle if the vertices lie on the circle. So we can say that the triangle is inscribed in the circle, whereas the circle is circumscribed about the triangle. So circum means around, and in means inside, and the scribed comes from the Latin scribo, which means to write, or I write. Okay, so here we have a pentagon that is circumscribed about the circle, and that means that each of the sides are tangent to the circle. And we can say that the circle is inscribed in the pentagon. Okay, that's what this part here is saying. Now, the center of the circumscribing circle is the circumcenter, and that's the same circumcenter that we found with our constructions. That's found where the three perpendicular bisectors meet. And the center of the inscribed circle is called the incenter, and that's the same incenter where the three angle bisectors meet in a triangle. Okay, so some theorems. A quadrilateral is inscribed in a circle, implies that its opposite angles are supplementary. We saw this already back last week with some of our examples that we did then. So B and D are going to add up to 180 degrees. A and C are going to add up to 180 degrees. And just so we're clear, a polygon that is inscribed in a circle is called cyclic. Okay, and I'll be using that word again later. Cyclic, like a cycle. So anytime I have a cyclic quadrilateral, opposite angles have to be supplementary. And this is the enjoyment part of the geometry for enjoyment and challenge. Please feel free to read the story about the plain old parallelogram named rectangle, and the following theorem just says that if I have a parallelogram inscribed in a circle, that parallelogram has to be a rectangle. And you can think about why that's true. Okay, so let's do some examples using that theorem and some of the other things that we have from this section. So in this diagram, angle A is 110 degrees. BC and DC are congruent to each other, and angle D is 95. So they want us to find a couple of the things here. So let's start with finding the measure of angle C. So angle C is across from angle A. It's an opposite angle with angle A. And the theorem we just saw says that those two angles, A and C, have to add up to 180 degrees. So that means that the measure of C has to be 70 degrees. Okay, now on to B. B is asking for the measure of arc BC. How are we going to find the measure of arc BC? Well, since chord BC and chord CD are congruent, that means that the two arcs also have to be congruent. And if you think about it, these two arcs together form major arc BCD, which is across from the 110 angle, the 110 degree angle that we were given. So that means that that major arc BCD is equal to 220 degrees. And since BC and CD are congruent, that's going to split the major arc into two equal parts. And so chord BC has to be 110. Okay. Now on to C. They want the measure of angle B. Well, angle B is across from angle D. Angle D is 95, and so angle B has to be its supplement, which is 85 degrees. And then for D, they want the measure of arc AB. That's not arc AB. How are we going to find that? All right. Well, angle D, which I have circled in green, is an inscribed angle, and that intercepts major arc ABC. So major arc ABC, this guy here, has to be 2 times 95 or 190 degrees. And we already found out that BC was 110. So if I just subtract those two, then I'm going to find out that arc AB is 80 degrees. All right, let's do another one. Okay, here in this circle, we're told that the measure of angle B is 115, and we're told that arc AD is 60. We also know that BC and EF are parallel to each other. Okay, so let's go through things. The first thing they want us to find is angle ADC. Angle ADC, this thing right there. Okay, well, that angle is an opposite angle in a quadrilateral from angle B, so it has to be its supplement. It has to be 65 degrees. That was easy. Now let's go to part B. Part B is looking for angle CDF. This angle right here, CDF. Okay, well, we just found that angle ADC was 65. We don't know what angle ADE is yet, but it is formed by a tangent and a chord, and it's eating an arc that's 60 degrees. So the angle, the measure of angle ADE, has to be 30 degrees, has to be half of the angle that it's eating. So now I have a 30-degree angle and a 65-degree angle. And so what's left for CDF? That has to be 85 degrees. So that's my answer to B, 85 degrees. All right, the next angle we're looking for is angle C. And that's simple because angle C and angle CDF are alternate interior angles with parallel lines. So angle C is also 85 degrees. And the last thing we're looking for is angle D, and angle A, part D, angle A, and that's across from the from angle C. So let me just get rid of some of this stuff here, just so we're not getting cluttered. So if we know that angle C is 85 degrees, angle A has to be its supplement, which is 95 degrees. And there we go. Okay, I have one more question for us to go through today. Here I have a quadrilateral that is inscribed inside of a circle. Now, I don't know if it's a rectangle, although I do see that angle Q is a right angle. They want us to find PS. Okay, so let's put in some side lengths here. We're told that PQ is 15, and we're told that QR is 20, and RS is 7. Okay, so clearly this is not a rectangle because RS and PQ are not congruent to each other. So we want to find PS. Maybe your first thought is, well, opposite sides have to add up to the same thing. Now, that only works when the quadrilateral is circumscribing the circle, or the circle is inscribed in the quadrilateral. So that's not going to work here. Instead, what we're going to do is we are going to draw in RP, which is a diameter. Now, how do I know it's a diameter? Well, angle RQP is 90, which means that arc RSP is a semicircle, and that makes RP a diameter. All right, and now I can use the Pythagorean theorem, or actually just a Pythagorean triple, to figure out that RP is 25, right? It's a 3, 4, 5. 3 times 5, 4 times 5, 5 times 5. And look at that. I have another triple set up for me for triangle RSP. But wait a second. I can't just assume that it's a right triangle. It would be nice if it were 7, 24, 25. But I do have to do some verification. How do we know that angle S is 90? Well, remember, opposite angles in a quadrilateral have to be supplementary. So if angle Q is 90, angle S is also 90. Ooh, that's a terrible box. And so I'm going to get a right triangle RSP. And yep, my 72425 triangle holds. All right, that's what I got for you. We'll see you next time.